details, but we're actually increasingly unified about what's going on. So I wanted to give you the sense of that. Computer, it's only the first. So I very briefly want to just run through these points, and I promise to go through them quickly. So although there are 7 points, we'll go fairly fast. The first one, climate change is real. It's caused by fossil fuels. It's caused by humans. We are unanimous as climate scientists in understanding that at this point. So I want to just show you this slide. It's a bit old. There's an updated version, but it shows the same thing. So what we're looking at here is how the temperature of the Earth has changed over the 20th century up until the early part of this century. And of course, the Earth has been warming. The critical point here is that if there had been no greenhouse gas emissions, no human influence, the Earth actually would have been cooling over the last 50 or 60 years, and that's even more so over the last decade due to a lot of natural cycles. So the fact that the Earth is warming is totally because of the greenhouse gases, carbon dioxide and methane primarily, that people are putting into the atmosphere, and we have a very good understanding of that. There's really no debate. The next point I want to make is that the climate change is accelerating. We're seeing consequences already. The consequences are severe and they're real. And the scientific community is increasingly willing to say that. So let me run through this in a little bit of detail. Again, we're looking at the warming of the Earth here from 1880 up until the present, pretty much. We're looking at this relative to the pre-industrial baseline of 0 degrees Celsius. So it's actually a little bit cooler back in time. It's been warming. The last decade has been the most rapid warming in the history of the Earth, 4 billion years. And each of the last 4 or 5 years have been among the warmest 4 or 5 years ever recorded in the last many, many hundreds of thousands of years. So the planet's warming, and 1 degree of warming is more or less where we are at the moment. That may not seem like much, but we are seeing major consequences from that. One of those, this is a summary of unusual heat events this summer from May through July of this year. And each of those little orange points there is a place where there's a record temperature on a particular day. And if it's black, then it's actually the hottest it's ever been on Earth at a particular time. We're getting more and more of these record heat events. That's not your imagination, it's true, and it's a result of climate change. It's not just record heats that global warming is causing. We're seeing stronger and more damaging storms, certainly hurricanes, but also winter snowstorms, more severe thunderstorms, more tornadoes. We're seeing record amounts of rain. There have been several instances over the last year or two where individual storms have produced the highest amount of rain ever seen. The hurricane that hit Hawaii just a few days ago produced record amounts of rain on the Big Island there, for instance. We're seeing record floods. We're seeing record droughts, and there's some real harm to agriculture already that we're seeing from that. Agricultural production this year looks to be depressed by about 15% compared to what it would be if we didn't have climate change. And we're having I'm calling this whiplashing. We go from a year which might have record rains to another year which would have record droughts, and this back and forth in an unprecedented sort of way. And that aggravates forest fires and brush fires. We're seeing massive fires in northern Scandinavia this year, throughout the American and Canadian West. In part, that's fed by the hot temperatures and droughts, but it's also fed by the rains of the previous season, which led to unusual vegetational growth, which can then burn. And we're also seeing an increase in nutrient pollution. The source of that's agriculture generally, but this whiplashing of really dry and really wet years aggravates that, and as we're seeing more and more harmful algal blooms as a result of that. So the consequences are real. The sort of things we're seeing have long been expected. They're predicted by the climate models. We've been predicting for 30 to 40 years that eventually climate change will cause the sorts of things that we're seeing. And it's just based on the physics of how the Earth's climate, the oceans and atmosphere work. If the atmosphere is warmer, it holds more moisture, and so you're going to get more rain. We understand that very, very well. Warmer surface oceans feed more energy and moisture into hurricanes and other storms, including snowstorms. So say in the northeastern United States, we've had some record snowstorms in recent years. Those are driven by the still cold but warmer ocean water off our coast in winter. And of course, we've lost a major part of Arctic Ocean ice. And that, together with the warmer ocean, has caused pronounced changes in the way the atmosphere circulates. If we look at the jet stream, the upper level steering currents in the atmosphere, we have more snakiness, if you will. The lengths of the jet stream, the meanders are longer, and they move more slowly. So they're bigger and they move more slowly. And that means that when we have storms, the storms sit in place longer. The weather fronts are moving more slowly, which is part of the reason we have these longer droughts. And that's a major part of what's causing that whiplashing of weather. Again, this is very, very well understood at this point. So the basic physics are leading to the weather we're seeing. This is from last winter. Large parts of the northern hemisphere saw really, really cold weather, polar vortex. That, in fact, is a predicted consequence of global warming because of the change in how the jet stream is working in the ice loss in the Arctic. Now, I really want to highlight this point. We scientists are trained to be conservative. We're not necessarily conservative by nature, but we have to be conservative. We get in a lot of trouble if we overstate what we know or what we have learned. And so a long time, climate scientists have all stated that you cannot say that a particular hurricane or a particular drought is a result of climate change. I want to emphasize that climate scientists are no longer saying that. We're now seeing enough in the way of effects of climate change that we know we're outside of what the world possibly could have been without the greenhouse gas consequences of humans. Statistically, the extent of the floods, the droughts, the rainfall events, the intensity of the storms, we just would not be having these unusually intense record-breaking events without the climate change driver. And we know that. And so the climate scientists are now much more increasingly, not unanimously, but most of us are saying that the large increase in the record weather events is in fact the face of climate change. This is what we expect. It is not a surprise. Very briefly, are we at the new normal? We've warmed the planet. We're seeing this change in weather. Are we now in a stable position? And we don't know, but probably not. Our models and understanding physics suggests that as we warm further, we're going to continue to transition the Earth, and what we're seeing now is simply one step in that direction. It's very, very likely that the effects of climate change will get worse, and probably far worse, and perhaps not in the far distant future. Which brings me to the topic of tipping points in the climate system and whether or not we might experience runaway, irreversible climate change. Most climate scientists believe that there are tipping points in the climate system. We have started to hit some of those, perhaps. As we hit more of them, we do run a very real risk of having climate change, which might take 5,000, 10,000, 15,000 years to reverse itself. So it's not irreversible, but it is on the time frame of human society. And this was recognized in COP21 back in 2015. And so there at COP21, the nations of the world agreed to try and keep the planet well below 2 degrees Celsius. There's a clear recognition, I think, among all participants there that 1.5 degrees warming is dangerous. We're at 1 degree now, and that is dangerous. So these are real worries. Where are we on that? Well, another look at what warming has been like over the last 100 years or so. We warmed in the 20th century. This shows actual data up to 2011 and then some projections into the future, and I'll come back and talk about those in a minute. But the reference line there, the top green line, is what we expect the climate to do if we don't really address greenhouse gas emissions. And I'd like you to notice that it's only 10 years from now that we'll hit 1.5 degrees warming, and we expect to hit 2 degrees of warming in the time period of 25 years or so from now. So these are not long distant targets, and those are very dangerous temperatures. What's the danger? Well, as we warm the Earth, we worry that the risk of hitting individual tipping points, whether they're melting of the Greenland ice sheets or the melting of the various Antarctic ice sheets or other changes, becomes more and more likely. And this was a projection as of 2007 from the IPCC as to what the risks might be of various potential tipping points as the Earth got warmer. And you can see that if we stay below 1 degree, the thought was that we'd have some worries about Arctic sea ice, but perhaps not too many other problems. Well, we are losing the Arctic sea ice at 1 degree. That's happening. And I want to go to the extreme right over there and talk about ocean circulation, which as of 2007, the climate scientists community was more or less thinking became a risk only when we hit 3.5, 4 degrees, maybe likely only at 4 or 5 degrees. Unfortunately, we are already seeing changes in ocean circulation at 1 degree. This was not expected. The oceans are more sensitive to climate than we would have realized a decade ago. And there's some real consequences of that, which I want to just briefly explain to you. This is sort of a simplification of the ocean circulation. If you look at the North Atlantic there, the left-hand upper side of that slide where the red arrow is coming up and the blue arrow is going down, what that signifies is that the North Atlantic water is sinking. We have warm tropical waters coming up and replacing it, and that water is sinking, going into the depths of the ocean where it moves slowly off to the Indian Ocean and Pacific Oceans, and it comes back to the surface on timescales of hundreds to perhaps 1,000 years or so. What's causing this is that the North Atlantic water is the densest, coldest water on Earth. It's cold and it's very, very salty, so it's heavier. That causes it to sink and be displaced by the warmer, somewhat less salty waters. We call this the great conveyor belt of the ocean, and it's important because it's redistributing heat across the planet. It's a large part of what causes the climate that we see and the weather, and when we get changes in droughts and floods, it's in part driven by changes in the circulation over short time periods. It also is very influential in helping to mitigate what humans are doing to global warming because it takes up a substantial amount of the carbon dioxide from burning fossil fuels into the oceans. That cold ocean water absorbs carbon dioxide, it sinks, it stays down in those bottom waters, again for hundreds to perhaps 1,000 years. Eventually it'll come back up, but it stays down there for a long time. And I have the slide here. I've changed it. If I'd given this talk a year ago, as I did, I would have said the great conveyor belt might be slowing, it might start to be slowing. We now know unequivocally that it is slowing. It's about 15% slower now than it was a decade ago. We know that with great certainty, and that's because of the melting of the Arctic sea ice and also melting of Greenland ice. That puts fresh water there into the North Atlantic. It makes it a little bit less salty and therefore not as heavy, and it slows that. So that changes our climate. It also changes the uptake of carbon dioxide, and it actually makes the oceans taking up less carbon dioxide. Computer's acting a little funky here. I just want to show you here, this is what's happening with carbon dioxide flows in and out of the Earth's system over time from 1850 up to the present. And you can see at the top there, we're burning fossil fuels and putting CO2 into the atmosphere, and we're also having deforestation, which releases it. The bottom part, the yellow there, shows the accumulation of carbon dioxide in the atmosphere. There's more and more there, but a large part of the carbon dioxide that we burn is not accumulating in the atmosphere. Half of it's being taken up by the land or oceans. And again, that seems to be slowing for the oceans, and it may be slowing for land as well. So another tipping point we worry about are more fires, and particularly places where there haven't been fires. And this shows a massive fire in the Arctic of Alaska about a decade ago. If we go back 20 or 30 years, there were never fires in the Arctic simply because, although there are things to burn there, there wasn't any source of ignition, nothing to start the fire. But with warming, we have more thunderstorms in the Arctic and more lightning, and so we have fires. This past year, there have been massive fires, say in northern Sweden and Finland, and those put a lot of carbon dioxide into the atmosphere. So that's very much of concern, and this is a bit of a complicated slide, but it's important for you to understand. We actually, as a planetary society, have been slowing our emissions of carbon dioxide from using fossil fuels. So for several years, 2015 through 2017, We're still burning too much in the way of fossil fuels, but it was not going up. Emissions were steady. Unfortunately, this year they're going up again. But even though they were steady for 2015 through 2017, the amount of carbon dioxide in the atmosphere still was going up, and it was actually going up at the fastest rate ever. And that is, we think, because of these feedbacks with oceans and fires and things, so that the storage, which used to be there, is no longer as effective. And this is an example of a runaway feedback that is quite scary to most of us. How am I doing on time, Shane?
We have we need to start wrapping it up soon. So
all right, let me take another, 3 or 4 minutes?
That's great.
Yeah. I want to just very briefly touch on the role of natural gas and shale gas, which increasingly is making up natural gas, at least here in North America, and fracking. So I just want to emphasize that carbon dioxide is not the only problem. Methane is also a major greenhouse gas. And in the interest of time, I'll go back to this slide, which I showed you before. I mentioned that if we do nothing with greenhouse gases, we've got that upper green line, and the planet will warm to unacceptable levels within the next decade or two. There are ways we can slow warming, and the ways to do it are the bottom 2 lines there. If we reduce methane emissions today, we slow the rate of global warming today. That is not true for carbon dioxide. And so, in fact, the only way to significantly slow warming over the next few decades is to reduce methane emissions to the atmosphere. We need to reduce carbon dioxide too, but we need to reduce methane. Now that's a big problem when we start looking at the idea of natural gas as a bridge fuel, because natural gas is mostly methane. Increasingly here in North America, we're getting our natural gas from fracking and shale gas development, and that increases the amount of methane emissions. And over the last decade, the methane content of the atmosphere has been rising at its most rapid rate ever. It's causing about 25% of the unprecedented warming we've seen over the last year. And the major source for that by far is shale gas development in the United States. It's globally significant in the warming we're seeing. Just quickly, if we look at this idea of natural gas as a bridge fuel, I'm showing you here the greenhouse gas footprint of various fuels normalized to the amount of energy that they produce. And the orange color there is the carbon dioxide emissions. Red is the equivalency of warming that comes from methane associated with using these fuels. And when you switch from coal or diesel oil there on the right to either conventional natural gas or shale gas on the left, carbon dioxide emissions go down. That's good, but methane emissions go way the hell up, and that is really, really problematic. So find the point. Is it too late? We have these effects already. We are accelerating the rate of warming. We are dangerous territory in the next decade or so. There's no doubt at all that we should have been reducing greenhouse gas emissions 40 to 50 years ago. And I hear people say, is it simply too late? Well, most climate scientists will tell you, no, it's not too late. It can get worse and worse and worse. So we need to reduce the emissions now in order to make a potentially manageable situation. And I actually am fairly optimistic that we can manage the problem as big as it is, but we need to move really, really fast. So what do we do fast? What's needed? I have some reason for optimism. What we need is a 100% transition out of fossil fuels into renewables. And in the interest of giving time for discussion, let me simply say that I and others work on that. Mark Jacobson from Stanford is a personal hero of mine. I've worked with him to come up with a plan which we published several years ago for weaning the state of New York off of fossil fuels. I think it's doable. It's doable on human timescales in a way that is affordable and actually good for the economy, good for people, good for jobs. So I'm optimistic we can do that and solve the problem. And if you have not heard, I wanted to mention that the California Senate and Assembly yesterday passed a bill to make California 100% renewable. California is the 5th largest economy in the world, and so this is really significant. The bill would call for it by 2045, which is a little slow, but it's definitely a step in the right direction. So very pleased to be able to talk to you. People there, I think there's time for questions. I can handle questions. Otherwise, let me know and I'll just stand by.